In the previous video, we stated the fundamental theorem of calculus, and here we're going to use it in a number of applications. Let's say that a particle moves along the y-axis with velocity 49 minus t squared, measured in centimeters per minute. We want to know how far does the particle travel in the first 7 minutes. This is actually the exact problem that we motivated the integral with in section 4.1. So we know that the distance traveled by this particle will be given by the integral of, so total distance traveled is given by the integral from 0 to 7, so that's the first 7 minutes, of 49 minus t squared with respect to t. Now, the fundamental theorem of calculus says to evaluate this integral, we need to find an antiderivative of this function here. So let's kind of try to work that out. We need some function f of t so that when I take its derivative, I'll get 49 minus t squared. Well, for a constant, kind of thinking about how derivatives work, we know we're going to have a 49t, since the derivative of 49t is 49. That would give us our first part. And then for the second part, well, we actually calculated the antiderivative of t squared in the previous video, and we know that an antiderivative of that form would be 1/3 t cubed. So this function, f prime of t, is equal to 49, since the derivative of t is 1. And then here, the power rule says this is minus t squared. So it's an antiderivative. So then the total distance is equal to 49t minus t cubed, evaluated between 0 and 7, which is equal to 49 times 7 minus 7 cubed minus 49 times 0 minus 0 cubed. Well, 49 times 0 is 0, 0 cubed is 0, so I'm not subtracting anything here. That's all, this all is 0. So this is equal to 49 times 7 is 300, and whoops, I made a mistake. Did anybody catch that? I forgot my 1/3. Let's stick that in here. 1/3. So there should be a 1/3 here, and this is divided by 3. Of course, it's still 0. Okay, so fixing that. But still, 49 times 7 is 343. And then 7 cubed is also 343. So this is minus 343 over 3, which is equal to 686 over 3. And what are my units? Well, dt is time, so it's minutes, and r of t is measured in centimeters per minute. So the minutes units on this cancels with the minutes units there, so all we get left behind is centimeters. Right? So the total distance is 686 divided by 3 centimeters, which is, again, if you go back to the video from section 4.1, that's exactly what we calculated using the hyperinteger definition. But now, so much easier. I can just use an antiderivative. But that in itself points out the value of finding antiderivatives. So in the next section, we'll devise a bunch of rules for computing antiderivatives. But here, let's just do a few exercises on finding antiderivatives. So let's find the antiderivative, or find an antiderivative. An antiderivative of, and we'll do a couple examples. So let's say first f of x is equal to 4 over the square root of x. I'm going to rewrite this so we can recognize, kind of like we would in derivatives, that this is some kind of power rule. And so I want to find some function whose derivative is this value here. So let's just kind of start by guessing. We know our power rule. So power rule is when I take derivatives, the power decreases by 1. So if we're doing antiderivatives, we're going to go kind of backwards. So my first guess would say, let's say f of x is equal to 4 times x. So I'm going to, instead of subtracting 1 as I would in a derivative, I'm going to do an antiderivative. So I'm going to add 1, and I would get a 1/2. Okay, so let's check. Is this an antiderivative? So if I take the derivative here, I need to get f back. I need to get 4x to the negative 1/2. Well, f prime of x, power rule says this is equal to 1/2 times 4x to the minus 1/2, which is 2x to the minus 1/2. Well, my powers are correct, right? I've got a negative 1/2 here, a negative 1/2 here, but my coefficient is not correct. It's a 2, and I needed to have a 4. So this isn't quite right. In fact, I'm off by a multiple of 2. So that was my guess. What I'm going to do now, instead of just keeping the 4, I'll multiply it by 2. Right? So let's try that. Let's say f of x is equal to 2 times x to the 1/2, or 4x to the 1/2, which is 8x to the 1/2. And if we take the derivative, f prime of x is equal to 1/2 times 8x to the minus 1/2, which is 4x to the 1/2, negative 1/2, which is our function. And so we see, oh, if f of x is 4 over root x, then its antiderivative is 8 times the square root of x. Okay? Let's take a look at another example. So let's say that f of t is equal to t squared minus t to the negative 2. So I want to find an antiderivative for this function. So my guess will be that, say, f of t, and I'm just going to kind of blindly do this. I know, again, power rule says that the exponent decreases by 1 in derivatives. So if I'm going to anti-differentiate, I'm going to do just the opposite. I'm going to add. So this would be t, say, t cubed. And same here, I'm going to add. So minus t to the minus 1. And now I'll check. Does f prime equal little f? So f prime, the power comes down. This is equal to a 3t squared. This power comes down, and I get a plus t to the negative 2. So I've got my powers correct. I've got a t squared and a t to the negative 2. My powers are right, but my coefficients of 3 and positive 1s are wrong. So I will try, so this was not quite right. So I will try a different, I knew my powers are right, but my coefficients were wrong. So let's try f of t is equal to, and come back, what happened? This power came down and became a coefficient of 3. I need my coefficient to be 1, so let's put a 1/3 in front, and that'll take care of when the power comes down and becomes my new coefficient. Similarly, my coefficient's wrong here, so let me subtract it and call this t to the minus 1. Now we'll check again. Well, or sorry, plus, because I need to be a minus. So let me check again. F prime of t will be equal to 3 times 1/3 t squared minus t to the negative 2, which is t squared minus t to the negative 2. And sure enough, that's exactly what my original function was. And so I found an antiderivative. So let's again kind of, and we'll spend some more time again in the next section really developing a strategy for finding antiderivatives. But again, let's use this in terms of the fundamental theorem of calculus. Let's calculate the integral from, say, negative 2 to 2 of x cubed with respect to x. So we want to know what is that derivative, or sorry, what is this definite integral equal to? And so we need to know an antiderivative. So my guess would be f of x. So it's a power of 3. If I'm anti-differentiating, I'm going to add this exponent. So f of x would be equal to x to the 4th. But hopefully from the other two examples, we know we've got to do something with this coefficient, because when the 4 comes down, I take the derivative, that would be my new coefficient. So I need, when this 4 comes down, it cancels out with something to give me 1 as my coefficient. So it's going to be 1/4. And sure enough, f prime of x is equal to 4 times 1/4 x cubed, which is x cubed. All right, so we've got an antiderivative. And so then if I want to calculate this integral, it is equal to 1/4 x to the 4th evaluated between negative 2 and 2. So that is equal to 1/4 2 raised to the 4th power minus 1/4 negative 2 raised to the 4th power. So 2 to the 4th power divided by 4 is 4. So this is equal to 4 minus, and when I raise negative 2 to the 4th power, it becomes 16. Divided by 4 gives me 4 again, so that's 4. And this integral is 0. Now, many students who first kind of start playing with integrals say, wait, how can the area under the curve be 0? But let's take a look at the graph of x cubed in between this domain. So we're going from negative 2 to positive 2, and the graph of the function looks something like this, and it's very symmetric about the y-axis. In fact, it's an odd function. And so the area between here and here, so this area would be negative, and this area would be positive. And when we add these two areas together, it gives us a 0 sum total area. So it's quite all right. Integrals can be positive, they can be negative, they can be 0. And that's the nature of it. The fundamental theorem of calculus says, well, it doesn't really matter about the function. Just as long as we can find an antiderivative of it, then we can evaluate it between its bounds of integration. So let's calculate one more example before we wrap this up. So what is the integral between 0 and pi of sine of x with respect to x? Now, this is another one that we looked at in the previous section, and we estimated this integral. If I recall right, we got that the estimate of this integral is approximately 1.9. But now we have the fundamental theorem of calculus, and all we need to do is find an antiderivative. Well, we know that derivatives of sine and cosine are linked, right? The derivative of cosine, well, that'll give us a sine, but the derivative of cosine is actually negative sine. That's not what we want. We want the positive sign. So if I make it a negative, then f prime of x would be negative sine of x, which is sine of x. So sure enough, negative cosine is an antiderivative of sine, and so this integral is just negative cosine of x evaluated between 0 and pi, which is equal to negative cosine of pi minus negative cosine of 0. And now just let me point out here, because this is too common of a mistake I see in students, is that the fundamental theorem says we've got to take the difference of the antiderivative evaluated between the bounds. And too often, especially if there's a negative involved, students will drop it and we would get the wrong answer. So I'm very cognizant that I've got to have a negative sign here. So usually, just to keep myself safe, I will write down the evaluation of the antiderivative on the upper bound, and then I'll immediately put in parentheses after the minus sign and write down the antiderivative again and evaluate it there. That way there's no room for mistake. Anyways, evaluating this, we know cosine of pi is -1, so this is negative 1. And then I've got a minus, so that becomes addition. And cosine of 0 is 1, and so this is equal to 2, which is what I told you in the previous section this integral was equal to. Now that we have the fundamental theorem of calculus, we can calculate it without even having to go to our Excel spreadsheet and get estimates. Okay, so that wraps up my demonstrations of applications. So one last thing I want to take a look at. So we've been using the second part of the fundamental theorem of calculus. We've been using the second part of the fundamental theorem of calculus quite extensively. What I want to do is do a few examples of looking at the first part of the fundamental theorem of calculus. So let me clear my board and just explicitly take the derivative of the integral function. So let's say that f of x, so our integral function, is the integral from 3 to x of sine squared of t with respect to t. So pointing out that some really important facts that are often overlooked by students. So my function f of x, its variable is x, and notice where that variable lives in the integral. It's here at a bounds of integration. This t is in some sense a dummy variable. It is just saying, look, I'm going to take values of t, put into the function between 3 and x, and multiply it by this infinitesimal value. So the variable, the thing that can change, is x, not t. So if I've got an integral function, f of x equals the integral from 3 to x sine squared of t dt, then the first part of the fundamental theorem of calculus says if I want to take the derivative of big F with respect to x, it's simply equal to the function that's inside of the integral in which we replace t with x. Students awfully find that that's way too simple, that this is just equal to sine squared of x. But that is what the first part of the fundamental theorem of calculus says, that if I have an integral function, its derivative is the integrand. In other words, this integral function is the antiderivative of this function sine squared. Now, that's not usually that helpful for us to find antiderivatives. We'll, again, in the next section, spend a lot of time developing rules, but this is very useful in applications. Now, let me kind of switch things up again a little bit here. Let's say that, I don't know, f of x is equal to 5, and the bounds will be 2x plus 7, and maybe my function is t squared plus 3t. And I want to know, well, what is f prime equal to? What is the derivative of f with respect to x? I cannot immediately use the fundamental theorem of calculus because my upper bound here is 2x plus 7. It's a function. But this fundamental theorem says if the upper bound is exactly the same as the variable, then the derivative is the integrand. All right, check that out. So I've got to be a little bit careful here. In fact, what I've really got is a chain rule going on. So let me give you another function. Let's define g of u to be equal to the integral of 5u t squared plus 3t dt. Well, now this is the right form. The u and the u, they're exactly identical. And so I know the derivative of u is u squared plus 3u. Well, what is the relationship between g and f? Well, f of x is simply g of 2x plus 7. So then f prime, taking its derivative, it is a chain rule, right? I've got a function inside of a function. So this is equal to g prime of 2x plus 7 times the derivative of 2x plus 7, which is equal to 2x plus 7 squared plus 3 times 2x plus 7, all multiplied by the derivative of 2x plus 7, which is 2. And so so going back, right, we just have that the derivative with respect to x of the integral of 5 2x plus 7 t squared plus 3t dt is simply equal to 2 times 2x plus 7 squared plus 6 times 2x plus 7. And so that's how the chain rule can work with the fundamental theorem. So that's sometimes maybe the fundamental theorem is not as straightforward like it is in the first example, right? If I just have the variable here and they're matching, then the derivative of big F is simply the integrand where I take t and replace it with x. However, if I have a chain rule here, so 5 to 2x plus 7, where the bounds don't agree, then it's still, the derivative is still, I put 2x plus 7 in for t, but then I've got to multiply by its derivative, by 2. Right? So it's still 2x plus 7 squared plus 3 times 2x plus 7, but then I have to multiply by the derivative of 2x plus 7 as well. Okay, so that wraps up the examples. In the next video, I will prove for you the fundamental theorem of calculus.